Practice question set 2A in preparation for quiz number 2 tomorrow here. Question number 1 says, the physical quantity that can have the same units as impulse. This should be a pretty straightforward one for us, right? What's the one that could have the same unit as impulse? Yep. It's got to be momentum, right? And the units would be kilograms, meters per second, or the other set of units we could use would be Newton seconds. Not newtons per second, but Newton times seconds. So 1D is the correct answer. All right, number 2 says airbags are designed to deploy when a car moving at a minimum speed of 18 kilometers per hour. We're going to circle that. Thank you, Adam, by the way. Comes to a crashing stop. The impact sensor, also moving at 18 kilometers per hour, consists of a small steel ball, 0.050 kilograms, which is held in place by a magnet, as shown above. On impact, the ball breaks free in this amount of time and slides within the cylinder. The ball makes contact with 2 electrodes, completes a circuit, applies an electric current, which ends up turning this powder, I'm not sure what the chemical is, this powder, into a gas really, really quickly and inflates this airbag. So it's not really an airbag, it's whatever gas it is that's generated when this electric current goes through this powder. We want to know the magnitude of the force required to break away from the magnet. We have time, and we're looking for force. So right away we're thinking force and time, we're thinking what? Impulse, right? We're thinking impulse. We have 3 parts to that equation. Delta P, the part that's not on your data sheet, F times delta T, and M times delta V, the 2 parts that are on your data sheet. We're looking for force, so probably going to use this part of it. We've got T, we've got M, and well, we don't have delta V, but pretty close, right? Okay, VF and VI. So we're going to use those 2 parts that do appear on our data sheet. F is equal to M times delta V over delta T. Now, some of you may have found delta P using M times delta V and then set that equal to F times T. That would be fine as well. All I'm doing is setting them equal to each other right now with the equations. What's M? 0.050 kilograms. Delta V is what? Delta V is if you don't think like deeply about this, you're just going to say, well, 18 kilometers per hour is a change in speed, right? 5 meters per second. And that's actually correct. If you think deeper about it, it becomes actually a little bit trickier. But it's still 5 meters per second. Here's the deal. This sensor and the steel ball, relative to one another, are moving at 0 meters per second. Agree? Because they're moving together, right? Just like when you're driving in your car, you're moving relative to the car at 0 meters per second. You slam on the brake and you don't have your seatbelt on, you keep moving at that same speed that you were moving relative to the road, right? So if I was moving at 5 meters per second and the car was moving at 5 meters per second, my velocity relative to the car would be 0. But then after I slam on the brake, my velocity would be, relative to the car, 5. Does that make sense? So I didn't really increase my velocity, but relative to the car, I increased my velocity. So what is the change in velocity? What is the delta V of this ball? 5 meters per second, right? Because it's now moving 5 meters relative to this sensor, and it was 0 meters per second relative to the sensor. So the change in velocity is 18 kilometers per hour, or 5 meters per second. My time interval here is 1 times 10 to the negative 3 seconds. We do the math there. The force works out to be C, 2.5 times 10 to the 2 newtons. Number 3, if the car was moving at 18 kilometers per hour, the maximum speed of the ball immediately after impact would be 18 kilometers per hour, or 5 meters per second. Be careful, though. Right? Be careful of that. Okay, those tricksters wrote this question. Did anybody put 18 meters per second, kind of being a little careless there? I'm surprised, actually, because usually that's what happens, right, is people know that sometimes, but they just put that one because they're just a little careless with units, right? 5 meters per second is the answer. Number 4, the car was initially moving at 18. The driver had a mass of 70 and the airbag stopped him in 0.10. What's the force on the driver? What's the force on the driver during that acceleration? Well, this is impulse as well. We're going to say force times time is equal to m times delta v. It's pretty much the same question as we did a minute ago, right? Except it's the driver this time. The mass of the driver is 70. The change in velocity of the driver would be 5 meters per second. Or negative 5 meters per second. The time interval is 0.1 seconds. Do the math there, and it works out to be B, 3.5 times 10 to the 3 newtons. And 5, one that I know messes people up. I've seen it mess people up before, including this semester when yesterday I think it was somebody was asking me about this one. The entire process from impact to airbag inflation takes less than 3 times 10 to the negative 3 seconds. That's pretty quick, eh? Like this airbag inflates very, very quickly. In fact, you know that an airbag has holes all around it. So it inflates so quickly that by the time your head actually hits the airbag, it's inflated and is actually in the process of deflating before your head ever hits it. That's how quick it is at inflating. Why, just as kind of an aside here for a second, why do they want the airbag with holes in it and to be in the process of deflating when your head hits it? Okay, if it was fully inflated, that would be better than hitting the steering wheel, right? But deflating is even better.
So that's more of a cushion, and it's more time that you're facing.
Good. It's more of a cushion. Okay, that's our kind of everyday answer to that question. But our physics or engineering answer to that question is just what you said after that, which is the idea that your head has a predetermined impulse, and if it's deflating, then it's kind of like cradling the baseball or basketball, right? Which increases the time that it takes to stop even more than just the airbag otherwise would, which decreases the force even more than the airbag otherwise would. All right, so during this same time, how far forward would a passenger who is not wearing a seatbelt move? Well, if the person not wearing a seatbelt would be moving at 5 meters per second for this amount of time, all we're going to do is say V is equal to D over T. D is equal to V times T, which is 5 meters per second, times a time of 3 times 10 to the negative 3 seconds, gives us a distance of 1.5 times 10 to the negative 2 seconds. So look at what that is, right? During this time of airbag inflation, you're moving at 18 kilometers per hour. Now, 18 kilometers per hour isn't particularly fast, right? Okay, but maybe it's a parking lot. Okay, 18 kilometers per hour. Your head moves forward during the airbag inflation 1.5 centimeters. Like that's how quickly the airbag inflates. Your head has moved 1.5 centimeters. Now, of course, if you're moving at 100 kilometers per hour, your head's moved forward a little bit more, right? But still, pretty quick inflation there. The answer is A for number 5. And practice question set 2B. Same types of questions here. Just wanted a few more to work on here. It says, at the starting point of a downhill ski race, the skier pushes with his arms and legs to get as fast a start as possible. The skier leaves the starting gate with an initial speed of 1.6 meters per second. The race course is made up of both steep and flat sections. At the end of the first flat section, the vertical distance from the skier to the finish line is 80 meters. That's the vertical distance, right? Still has 80 meters to go down. And the skier has a speed of 20 meters per second. At the end of the steepest section, the skier reaches a maximum speed of 33 meters per second. I'm just going to cross this off. Right? They give me a break here and they convert it for me, right? I'm never going to use the kilometers per hour, so I might as well just cross it out. The mass of the skier is 68.2 kilograms. What's the magnitude of the impulse as he leaves the starting gate? It's important to recognize that, right? Because there's a couple different things happening here. Leaving the starting gate, flat section, steep section. Okay, we want to analyze leaving the starting gate. clearly an impulse question because it asks us for impulse. We're going to use probably m times delta v because we don't know anything about the force. The mass of the skier is 68.2 kilograms. What's the change in velocity of the skier? 1.6 meters per second. Now, this can be a little bit confusing because it says here the skier leaves the starting gate with an initial speed of 1.6, but yet I'm calling 1.6 the final speed right here, or the final velocity. Yeah? Right. The actual initial speed in this whole problem is 0 because he's at rest, right? Now, the initial speed going down the hill is 1.6, but that's the final speed if we're talking about the gate. So I don't know if they did that, or they called it the initial speed just to kind of see if we could interpret that or to throw us off or what. But recognize that just because they call it the initial doesn't mean it is the initial for the part of the problem that we're dealing with. Okay, it is the final. We do the math there, works out to be C, 2.27 times 10 to the 3 Newton seconds. Now this one, this question, sorry? What is it? Is it A? Okay, A, 1.09 times 10 to the 2 then. Changed my mind. When you do the math there, this math, you end up getting A? Okay, I must have just circled the wrong one for whatever reason here. Okay, I'll trust you on that. This is democracy in action, right? Okay, you guys vote that A is the correct answer? All right. The voters are never wrong, except when they are. Okay? The voters are always right, except when they're wrong. Okay? That never happens, right? That hasn't happened any time in the past few years where the voters have been wrong, right? Never. Okay, now this is a hard one. This one says a full draw is a maximum distance that an archer can pull back an arrow using a recurve bow shown below. A particular archer requires an average force of 130 newtons to pull a full draw of 70 centimeters. Centimeters, we don't want centimeters in anything we do, right? Then it says the mass of the arrow is 20.6 grams. We don't want grams either, we want kilograms. So draw attention to that stuff, right? The question on the next page says, when the archer releases the arrow from full draw, the magnitude of the impulse that the bow gives to the arrow is what? All right, we want to find the impulse. If I want to find the impulse, I'm going to use either F times T or M times delta V. I know the force, I don't know the time. I know the mass, I don't know delta V. My gut on this, and I'll tell you what, like you're not going to be wrong by picking one of those equations to go with it, right? They're valid, like they're all valid. But my gut on this is to try M times delta V. So that's what I'm going to go with, M times delta V. If your gut was to try F times T, try it. And if you can't make it work, then try the other one, right? Like you're not wrong by trying the other one because they're both valid. I know what mass is here. The mass here is 0.0206 kilograms. But what's delta V? Well, VI is 0, right? VI is 0. VF is, I don't know. I got to figure out what VF is. Here's what I'm going to do to find VF. Now, this is something that we don't have to do very often in Physics 30. It is a Physics 20 concept, but remember what we said the other day. Sometimes we get a question where we need to do something from Physics 20. There'll never be a question that says, like a projectile motion question, let's say, in Physics 30. We're not going to have a Physics 20 question, but sometimes we have to do Physics 20 stuff as part of a Physics 30 question. Does that make sense? This is one of those questions, or at least that's the way that I tackled this one. But remember what we also said, whenever we run into a situation like that, or potentially run into a situation like that, I try to give you an example or some examples in class to remind you of that concept so that you're not surprised on a diploma exam by needing to do some physics 20 concept that you haven't done in 12 months or something like that. So we can't promise that. Okay, I can't, because sometimes they're good at coming up with new novel questions, but we do as much as we can with that. So here's what I want to do for this. I want to use work. And the reason that I chose to use work here, for me, it's a little bit easier because, I'm teaching physics 20, so this stuff is fresher for me, right? But I see force and distance. Remember, work is force times distance or force times displacement? But remember what it's also equal to? Delta E. Remember that? So what I'm going to do here is say force times distance, or force times displacement, is equal to, well, delta E is, the change in energy is kinetic energy minus 0. Make sense? If I multiply the force times the distance, then I'm going to get the total energy that's given to this as I pull it back, and then as I release it, it's going to end up being converted to kinetic energy and solve for VF there. So I'm going to say, knowing this, solving for VF, I end up getting a VF there of 93.9944 meters per second. Did anybody else get 93 meters per second a different way? Oh, quite a few people.
I thought acceleration.
Okay.
Force and mass.
Okay, so after, yeah, okay. And then, so you said A is equal to F over M. And then you said probably VF squared is equal to VI squared plus 2AD. Okay, yeah, absolutely, that would be fine. And probably a little bit more familiar with you, for you too, but does this make sense, though, guys? So it wasn't required. That's just, for whatever reason, that's what came to my mind, probably because of the force and the distance. But certainly there was another way to do that as well. Okay, now we're going to multiply that, 93.9944 minus 0. Do the math there, and that works out to be 1.94 Newton seconds. Now, I want to draw your attention to something here, okay? We will get the last two questions of your diploma exam, the 49th and 50th question, okay? One of them will be just like a numerical response question, and then the other one will be a question that asks, which physics principles did you use to solve this problem? And what do we mean by which physics principles? Well, if you take a look in the bottom left-hand corner of your data sheet, I'll ask you to do that now. Bottom left-hand corner of your data sheet, right here, there's a list of 10 physics principles. And we'll spend some time as the semester goes on talking about these physics principles and so on. But tell me, if I use this to solve this problem, can you tell me, looking at that sheet, which physics principle that would be? I don't have the list in front of me, actually. Just so, don't give me the number, tell me the words. No, we wouldn't say conservation of momentum, no. Yep. That's called the work energy theorem. Okay, does that make sense? Work is equal to the change in energy, the work energy theorem. Now, there was a handful of you guys that used F is equal to M times A. So what was the work energy theorem? What number was that? 3? So I used principle 3. Okay, some of you used what principle? If you used F is equal to M times A, we'd call it, sorry? Accelerated motion principle, I think that's 1. Principle 1? Okay, so some of you would have used principle 1 instead of principle 3. Okay, and both of those would be keyed correct on the exam because both of them are legitimate methods. Does that make sense? Okay. All right, is there any more questions? Yeah, one more, I guess. finish off with a nice easy one here. A rock climber falls and is safe from injuries by a climbing rope that's slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse because elasticity results in what? Well, what are we trying to do? We're trying to stop this rock climber, right? When we try to stop an object, the idea is to, the impulse is predetermined, the idea is to increase the time which decreases the force. So the answer is going to be A for that one. Decreased force during an increased time interval, impulse staying the same. All right?